Let's look at sets of numbers. All the numbers you've encountered so far in your maths career we call real numbers, and sometimes they're represented by the symbol R. Now, you may not believe it, but beyond real numbers, there is a group of numbers that we call imaginary numbers or complex numbers, and you'll learn more about those in Year 12. But let's think now of the numbers you've encountered so far. Way back, you learnt first of all about the counting numbers, 1, 2, 3, 4, 5, etc. Those numbers we call natural numbers, and if we want to represent them, we use the letter N. Then in about Year 7 and 8, you added in the negative numbers and 0. So all of the negative numbers, 0, and all the positive numbers, we gave a name to called integers. And representing them, we represent them, you may not know this, but by either the letter J or sometimes Z. The natural numbers made sense, doesn't it? N. Real numbers made sense, R. But integers, for some reason, they've given the letter J or capital Z. Now, a set which encompasses those numbers or includes those numbers plus a whole lot more is the rational numbers. Now, what are rational numbers? A rational number is any number which can be expressed to a fraction, or it also can be expressed as a terminating or recurring decimal. Here's some examples to show what we mean. 3/4 obviously is a fraction, and it can be expressed as a decimal point 75, which terminates, it ends after the 5. So that one's okay. If we say 20%, we know 20% is 20 over 100, there's your fraction, cancel it to 1/5, and we also know that 20 over 100 or 2/10 is 0.2, so expressed again as a terminating decimal. If we express a number first as a decimal, which does terminate, we know we can change it to a fraction. 1.2 is 12 over 10, which cancels to 6 over 5. A little more complicated is fractions like 5/7. If you do that on your calculator, you'll find it's 0.7142857142857, etc. If you listen carefully to what I said there, you would have seen that there was repeating decimals. 7142885 is then repeated again and again. So 5/7, the fraction, can be expressed as a terminating, no, not terminating, can be expressed as a recurring decimal. These numbers belong inside the set, don't they? Because we can express 2 as a fraction as 2 over 1. 0, we could express as 0 over 1 or 0 over 5, 0 over anything. -4, we could express as -4 over 1 or 4 over -1. It's expressed as a fraction, isn't it? That's why these sets belong inside the set of rational numbers. They're special cases of rational numbers. But you've also come across other numbers which can't be expressed as a fraction. They're called irrational numbers. Can't be expressed as a fraction, and therefore also they can't be expressed as a terminating or recurring decimal. One number you've come across like that is pi, which you've heard is 3.14159, going on and on and on forever. And computers continue to churn out the decimal places, but nobody's been able to find a pattern to those decimals. In other words, it doesn't terminate and it's not recurring. Another one you'll come across in Year 12 is the number e, which again is a bit like pi, 2.71828, and it continues on and on forever with no pattern. But there are others that we come across in the work on Pythagoras' theorem, numbers like √2. If you look at √2 on your calculator, you won't see any pattern to the decimal points. √3, √5, √7. You noticed I missed out √4 because √4, of course, is 2, which is a natural number, therefore it's not one of these. The next one I miss out, of course, would be √9, then √16, but all others in between those will be of this form. They will not be able to be expressed as a fraction. They can't be expressed as a terminating or recurring decimal. So they're also examples of irrational numbers. And in fact, these are given a special name. They're called surds. And that's the subject of our extension unit that you're about to study.